Here we go. Okay, well, thank you everyone for joining us here this late morning, early afternoon for another webinar presentation we'll be conducting today. I'm Gary Osmond. I'm the local field engineer here for Swagelok Pittsburgh. And our presenter today will be Scott Banfield, Swagelok account manager here for Swagelok Pittsburgh. Our topic today is pressure gauges and gauge failure avoidance. So some best practices and things to consider when you are using pressure gauges in your system. So Scott will get into much more detail here for the next 25, 30 minutes. So just a couple housekeeping things. We will prefer to have everyone have their microphones muted for the duration of the presentation. Feel free to use the chat function if you have any questions, comments, concerns throughout. And then on the back end of the presentation, we'll have a little Q&A session for as long as we need, really. You feel free to unmute and chime in with any questions that you do have from the presentation or any comments or things you'd like some further information on. We can always follow up on afterward if needed. And you can use the chat function during that time as well. But for the time being, I'm going to kick it over to Scott. He'll run through a presentation and then we'll circle up on the back end and see if anybody else has any discussion points and go from there. So thanks again, and kick it over to Scott.
All right, thanks, Gary. Hi, everybody. Thanks for joining us again today. And my name is Scott Banfield, and my official title here is Field Sales Representative. I live and work out of a home office in State College, so I kind of cover accounts in the central Pennsylvania area. And I'm excited to talk to you today about gauges and some of the issues that we see out there. We wanted to do this webinar because most of us at Swagelok Pittsburgh have seen how gauges are misapplied in various plants and at customer sites, and it's apparent that they're often not given the same consideration as other instruments. They are a critical instrument in any system, however, so we wanted to present this info with the hope that you might gain some insight from it as to what some of the common issues with gauges are and how to solve them and avoid them. So with that, this is what our agenda looks like today, and we're going to be focused mainly on number 2 here. As Gary said, we're going to be talking about common causes of gauge failures and what some of the solutions are for those issues. For the rest of the items, it'll just be a couple slides, really, and we'll move through that pretty quickly, and we should be no longer than a half hour, like Gary said, and also use the chat function or the hand raising. Everybody's muted, so if you have any questions or comments during the presentation, Gary can let me know and we'll pause and address those as we go. So let's start off here with how a gauge works. So when you talk about analog mechanical gauges, the vast majority of gauges use a board-on tube design. So there are some other types of gauges, but this is primarily what you see out there. So just to give you an idea, if you don't already know how a gauge works, the board-on tube design uses a board-on tube, which is a piece of tubing that you see right here, this circular shape, and it's connected to the inlet of the gauge, and it's sealed off on the other end. So your system pressure is going to enter this board-on tube. And being a curved piece of tubing, when you apply pressure to it, the curved piece of tubing wants to straighten out. So as the pressure changes, the sort of diameter of this tubing is going to change, and that moves a link here, which is connected to a pinion gear that's connected to the pointer. So as the pressure changes and the board-on tube moves, it moves the dial on the gauge and changes your pressure reading. So that's kind of the nuts and bolts of how the gauges work, board-on tube design, and go right into common causes of gauge failures. We're going to talk about each of these separately here: mechanical vibration, pressure-related issues, which would be pulsation, pressure spikes, overpressurizing, temperature concerns, corrosion concerns, clogging can be an issue, and then also mishandling and abuse. So we'll go right into mechanical vibration here. So mechanical vibration is caused by an external source, usually a piece of vibrating equipment that's near the gauge. Typically, it's going to be a pump or some type of rotating or reciprocating equipment, which tend to cause a lot of vibration. And the issues that you have is that it increases wear on the movement and internal components of the gauge, and it makes it difficult to read the pressure because vibration usually translates into the gauge as the needle fluttering, so it's harder to read. We're also going to talk about, as I said, pressure, pulsation, and everything we talk about here in vibration is going to be very similar to pressure pulsation, but pressure pulsation is a little bit different, and we'll get into that shortly here. So with mechanical vibration, here's some examples of what you might see. This is the pinion gear I mentioned that would be connected to the dial. You can see how the splines on the gear are worn in the middle there. And then the gear on the right that would be connected to this pinion, you can see how the teeth are worn. They're all from just a heavy vibration in the system. Some other issues that vibration might cause is wearing on the link. A normal link is a round shape like this, whereas a worn link, you can see how this one is kind of ovaled out, and that's going to make your gauge less accurate. You can also see here how you have a crack in the board-on tube, so a heavy vibration can actually crack the board-on tube, and then you've got a complete gauge failure and leakage of your system fluid. And in this example here, you can see there was enough vibration that ultimately it caused the needle to fall completely off of the pinion gear, and it's just laying in the bottom of the gauge casing there. And you can also get a sense how there's some dust and debris inside the gauge that's also come from the vibration. So the solution to vibration is a pretty simple one, liquid fill. There are lots of gauges out there that have the ability to be liquid filled. And I'm going to show you a quick video here that demonstrates the impact of the liquid fill. So check this out, and you can see how much difference it makes when you use a liquid fill. So at the top here, you can see there's a port on the gauge where you put this, probably glycerin they're putting in there, and you can see the glycerin running into the gauge, and here it starts to fill up. And you'll see the impact as soon as it reaches the bottom of that needle there. See, immediately the fluttering is reduced. And then I'm going to fast forward here a little bit for the sake of time. You can see once the gauge is almost full, the needles completely stop fluttering. And then at the end here, the video backs off and it shows you a comparison to the gauge next to it. So that's a pretty cool video, good demonstration of how the liquid fill solves that problem. Moving on here to pressure-related issues such as pulsation, pressure spikes, and overpressurizing the gauge. When we talk about pulsation, like I said, this is similar. It affects the gauge similarly to vibration, whereas there's a lot of needle fluttering. So it's caused by your system media rapidly cycling the gauge, and it increases wear on the internal components and the board-on tube. It makes it difficult to read the pressure gauge because the needle's fluttering, just like in the video you just saw. And if the pulsation increments are greater than 5% of the full scale value, you have to intervene to prevent damage to the gauge because it's ultimately going to fail. So when we look at a gauge like the one in this picture here, you have a 300 PSI gauge. 5% of that is going to be 15 PSI. So if the needle's fluttering more than 15 PSI, you've got to solve that problem or the gauge is going to fail. There's a couple different kinds of pulsation that you see out there. Centrifugal is a high frequency, low amplitude pulsation. So what that means is the needle flutters very fast, but not as far on the gauge as a reciprocating condition. Reciprocating would be more low frequency, high amplitude. So the needle is moving very far, but not as fast as it would in a centrifugal situation. The types of failure that you might see from this are a split in the board-on tube, which you can see on the left here. You can see that crack there, and then a cross section just shows the same piece of tubing there and where you can see the crack there. So when we talk about spikes and overpressure, the difference on the graph on the left here, overpressure is a sustained condition. So the gauge has been pressurized beyond its rating and held at that pressure versus a pressure spike where it's a rapid increase in pressure, but then goes back to normal. You're seeing a sort of a surge in the system that comes and goes that causes the gauge to spike. In general, an overpressure failure is caused by the application of a pressure greater than the rated capacity of the measuring element. So if the gauge is rated to 600 PSI and it's seeing 1,000 PSI, that's an overpressure situation. In some cases, ultra-fast pressure increases can cause the pressure element to fail well before its rated rupture pressure. So if the gauge is rated at 600 PSI and it's seeing pressure spikes maybe from 200 to 500 PSI, you're still within the pressure rating of the gauge, but those spikes can still cause a rupture just because of the way the pressure kind of slams the internal components of the gauge so quickly. And here's some examples from spikes and overpressurizing the gauge. On the left, you can see that the bourdon tube here is actually completely misshapen. It doesn't match the curvature of the gauge case anymore. And you can also see where it's split on the end here, and then a more close-up picture of how the end of the tube is split. So solutions for these pressure conditions here. For pulsation, the solution is the same as vibration. Just like in the video you saw, liquid fill will solve that problem in most cases. For a more severe pulsation and also for pressure spikes, you can use a snubber with the gauge. So this is an attachment that goes, the gauge goes into the attachment and the attachment goes into your system. And what it does is it creates a sort of a buffer there. With a porous snubber, you have kind of like a porous filter element that just dampens the pressure before it reaches the internal gauge components. And with a piston snubber, does the same thing in a different way. It utilizes a piston design. And then the adjustable snubber, if you can see in the picture here, it's actually like a little needle valve. You can adjust this set screw that has a a needle valve type shape on the tip that just changes the orifice to dampen the pressure. And along those lines, you can also use a needle valve for pulsation and pressure spike situations. You just would install it below the gauge, and you can use the needle valve in the same way as we just saw on the last slide here on the adjustable snubber. So for overpressurization, one option would be a relief valve. Relief valves can be adjusted to a wide range of pressures, and they can be relieved to atmosphere or captured and returned to the process or flare. So the relief valve would be adjusted to the pressure, and then when the pressure in the system when you're overpressurizing the gauge and the pressure in the system rises, the relief valve will then vent off the excess pressure, as it says here, either to atmosphere or you can capture the release gas also. There are also overpressure protectors that are specifically for gauges. And basically the way these work is they are adjustable as well. And when the pressure in the system reaches a certain point, the overpressure protector will essentially shut off. It's like a shut-off valve to the gauge where it'll block any of the overpressure from entering the gauge components. So the next mode of failure here would be temperature extremes. And this is a pretty dramatic picture here. The point of this picture is just to demonstrate how we're not talking just about the temperature of your system fluids, but also the ambient temperatures are just as important. In this case, the gauge was put in an area that was so hot that it caused the plastic case around the gauge to melt. And there are lots of industrial applications out there where you really need to take those ambient temperatures into consideration. So solutions for temperature-related issues. I mean, obviously, you want to ensure that the ambient temperatures and immediate temperatures are within the allowable limits of the gauge. You know, with any gauge, you're going to have that data out there as to what the ratings are for the process temperature and also the ambient temperature. And when you have excessive process temperature applications, you may need to use accessories we're going to talk about here in a second, like diaphragm seal or some of these other ones listed here, like a pipe extension or a steam siphon. If it's a steam application, there are different types of cooling elements and cooling towers, and diaphragm seal as well. And this will give you a little bit of an idea. So the picture on the left here, this is a typical steam siphon that you would use in a steam system. And what that does is basically as the steam heads up towards the gauge, and it condenses, turns to a liquid, this circular piece here will fill with that liquid, and the liquid acts as a barrier so that the hotter steam cannot actually reach the internal components of the gauge. On the right side here, we have just a diaphragm, an accessory shown, and then this is the diaphragm accessory with the cooling element. So this example they show at the bottom here, a 500 degree Fahrenheit system. On the right, you have a 750 degree Fahrenheit system. So they've also used a cooling element, a different type of cooling element. But as you can see, it's a longer element. So the size of the element may change depending on what the temperature is. So a few examples there. Moving on to corrosion. So corrosion failure from media attacking the wetted parts material of the pressure gauge. So basically, if your system fluid is not compatible or highly corrosive, eventually you may end up with actually eating holes in the board-on tube like you see here. So you end up with a complete failure and leaking system fluid. So you always need to make sure that the internal components are going to be as compatible as possible with your system fluid. And it's not necessarily just the system fluid, but again, the environmental, the surrounding environment, you need to be aware of that also. Because as you can see in these pictures, on the left here, we have the dial face. This is probably aluminum, and you can see how it's starting to deteriorate along the bottom because it's exposed to corrosive environment. And then this one here, obviously the gauge window is just completely unusable at that point. You can't even see the dial because of the ambient situation with corrosion. So corrosion solutions want to ensure that the wetted parts material, the case material, and the internals of the gauge are compatible to your system media and the atmospheric conditions. Excessively corrosive media applications may require the use of a diaphragm seal, and that's what you see on the picture here. The diaphragm seal is going to isolate the gauge components from your system fluid. And moving on to clogging. So media does not have to be aggressive or hostile to require the use of a diaphragm seal. So here's a Hershey chocolate bar example. In the food and beverage industry, if you're talking about chocolate, it's liquid when it's warm, but when it's cooled, it becomes a solid, and it will clog components, including gauge. And I could give a more real life example. I guess for me, I handle a refinery up in Warren, Pennsylvania, that makes gasoline, and one of their products up there also is asphalt that's used for like paving roadways and also in shingles and things like that. And the asphalt is it's liquid when it's hot, and when it cools off, it becomes a solid. So they're very cautious up there in the asphalt system as to how that affects those components. And certainly with gauges, you would need to use a diaphragm or something that's going to isolate that system media from the gauge components. So, and that's what we're showing as a solution here. This picture shows a diaphragm that's been added to the gauge and will protect it from any kind of media that could cause a clogging issue. So mishandling and abuse, you see this quite often, especially in large industrial type plants. Here's an example of a cracked case, and that could be, somebody hit it with a toolbox or a tool accidentally, or you might have a broken window like you see over here. And that's just an awareness thing and being cautious, but there are some options here. You can see there's protective cases you can get that go around the outside of the gauge. That'll help. One other thing that we see sometimes is that installers out there will use the gauge case to tighten the gauge sometimes. So essentially they're going to grab it with their hands and just twist it into place, which is certainly not meant to do that. Pretty much all gauges have flats on the end connection like you see here, and they're meant to be installed with a wrench. So definitely want to use a wrench on those. So proper gauge selection. Just to considerations here, as with any system component, there are certain things you want to keep in mind when you're selecting a gauge for an application. Size, obviously, if it's something that's you need to read from further away, you might want a larger gauge. Temperature, like we talked about, general conditions within the application, the media, if it's corrosive, what the pressure range, which we're going to talk, there's another slide on that in just a second here, but the pressure range needs to match your system pressure. The end connections are a consideration, and the delivery time too. With specialty gauges, sometimes they're going to have longer lead times, and that's something you want to be aware of. So with the dial range, ideally you want your needle to fall in the middle of that dial range. So what that means is, in this example here, if you've got a 500 PSI system, you want to use a 1000 PSI gauge, and that's going to put your dial right in the middle. It's acceptable to work within the middle 50% of the gauge range. So as it's shown here, between 250 and 750 for this gauge. That's acceptable. Ideally, what you're shooting for is the center of the gauge, which in this case would be 500 PSI. Wanted to mention briefly a tube adapter end connection. This is something that's kind of unique. You may not have seen it before. So if you've ever used Swagelok fittings that have a tube adapter end, we apply those to gauges here also, and there may be other gauges out there that use them as well. But the benefit of these is that they solve alignment problems, which are a pretty big problem with gauges. You know, most gauges have an NPT connection like you see here. And when you install those gauges, you turn those NPT threads, and when you've tightened them properly, the gauge is almost never facing the right direction. So ultimately what you end up doing is either over tightening the gauge so it's facing the right way, or under tightening it. If it's really close to where it needs to be and it's close to being tight, you may not feel like you can get another full turn. So you may leave the gauge slightly under tightened. And those are both not good situations. You could end up with leakage in either case. When you over tighten the gauge, you can stress the threads and compromise the fittings and cause leakage. So with the tube adapter, this solves those problems by, like you can see left here on the left side, you can use the tube adapter with the Swagelok fitting on a tubing system and eliminate the MPT threads altogether. Or you can use it with the MPT threads where you would tighten them as you should, following all the proper procedures. And then in order to align the gauge, you just loosen the Swagelok nut, turn the gauge so it's facing the right way, tighten the Swagelok nut, and you know, everything is installed properly, and you shouldn't have to worry about leakage issues or other issues that come with you know, improperly installing the MPT threads. So a brief rundown on the Swagelok gauge offering, just to make you aware, if you didn't know that Swagelok does offer gauges. This is just to give you a real quick one slide overview here. We have dial sizes from 1 to 6 inches. We cover pressure ranges anywhere from vacuum to 15,000 PSI. We do have application-specific models that would be used, for example, in an ammonia system, natural gas vehicles, which would be CNG, sanitary applications, which would have a special fitting that's used in the sanitary industry, and also ultra-high purity, where the gauges would have special cleaning specifications, and also particular type of end connections that will be used in the high purity industry. We also offer liquid filled and unfilled gauges, many different panel mounting options. We do have safety models that are used for severe service. They're designed to, if they fail, they will blow out from the back side of the gauge instead of the front. So if there's, you know, it's better safety for an operator in that situation. We have various different end connections and mounting configurations. When we say mounting configurations, go back to this previous slide here real quick. So this here would be what we call a lower mount. And there are also a center back mount where the end connection is off the back of the gauge in the middle, and there's a lower back mount that is also on the back of the gauge, but at the lower end of the gauge. So those are some different mounting configurations we offer. We do offer snubber fittings and some steam coil siphons like we talked about previously, and we have pressure transducers as well. So that pretty much sums up the content there. I'd like to open it up for questions or comments. If anybody has anything, we'd love to hear from you. I'll turn it back over to Gary, and maybe he can unmute everybody if anyone wants to chime in.
Yeah, Scott, great job. Appreciate the presentation there, and hope everyone was able to follow along and pick some things up. But certainly we have a couple of minutes. You did great on the timing. If anybody else has something that they want to question or just chime in about, or maybe see additional information on, feel free to unmute or use the chat function. We'll hang on for a minute or so here just to give some people some time to put their thoughts together and ask anything that might be on their mind based on that. But that was a really well done presentation, Scott. I think to just kind of recap a little bit on your point there, pressure gauges do a lot of the time go overlooked, and they're not really given the consideration that is warranted when they're installed into a pressure system. So taking all the considerations into effect and realizing there are a lot of options and accessories that can go with them to really make them perform and function as intended is really critical. So keeping all that in mind is important moving forward, I would say. Okay, well, not an overwhelming slew of questions here, but like we said, this has been recorded, so it'll be shared with everybody attending. You can reference it in the future or share it with anybody else you think that would be interested. And that's pretty much it. So thanks, Scott. Great job today. And kind of looking forward, I guess, for everybody on the call here, the next edition in our series of Swagelok Pittsburgh webinars will be valve selection and safety. And that's going to be on August 25th, presented by Bob Sarber, as you can see on the slide here. So I guess mark your calendars or keep that in mind. We'll be sending out the registration and invites for that in the coming weeks or so. So we'll make sure that we get them out to you and spread the word to anybody else you think might be interested, so they can attend as well. So thanks again, everyone. Hope you enjoy the rest of your day. Thanks for spending a little bit of time with us, and hopefully it was beneficial to you. If you do have any questions or comments you think of later or want to follow up with a note or whatever, feel free to send myself, Scott, or anybody else an email or give us a call and let us know what you think or what questions you have, and we'll take care of you. But again, appreciate your time, and have a good day.
Yep. Thanks, everybody. Thanks, Gary.
Thank you.
Thanks, guys.
Thanks.